Nucleophilic substitution reactions are an important class of organic reactions, and both aliphatic system and aromatic system undergo this type of reaction. Now in this video we'll be discussing one of the aromatic nucleophilic substitution reaction, that is Benzyne mechanism or elimination addition mechanism. As you may be aware that usually the aromatic ring do not undergo nucleophilic substitution reaction, or it's not very common with the aromatic system. Nucleophilic substitution reactions are not very common with the aromatic system. Now the replacement of a hydrogen or a substituent on the aromatic ring by a nucleophile is the aromatic nucleophilic substitution reaction. Now, why is that it is not common with aromatic systems? Because the aromatic ring has got an electron cloud above and below the ring. And so this ring will shield, this electron cloud will shield the carbon ring from a nucleophilic attack. Or you can say that this electron cloud will repel the incoming nucleophile, which is negatively charged. Now another reason which we can attribute towards this low reactivity of aromatic system towards nucleophilic substitution reaction is the presence of lone pair on the leaving group, or a pi bond on the leaving group. This lone pair of electron, if present, or the pi bond if present, will take part in the resonance, and hence the leaving group and the ring bond will be more, it will be double bonded, and it will be more firmly, the leaving group will be firmly bonded onto the aromatic ring. So because of these two main reasons, nucleophilic substitution reactions in an aromatic system is not common. But we can make it reactive, we can make the ring reactive towards nucleophilic attack by carrying out the reaction in drastic conditions like using high pressure and high temperature, or using a catalyst during the reaction, or introducing an activating group, an electron withdrawing group, ortho or para to the leaving group, or by making the leaving group using a very good leaving group on the aromatic ring, you can carry out the reaction. Or the reaction can be carried out by introducing a heteroatom to the aromatic nucleus. Now in Benzyne mechanism, or the Benzyne mechanism happens when the aromatic ring do not have an electron withdrawing group on it. Now this nucleophilic substitution reaction on aromatic compound are of four types. That is a Seneca mechanism, addition elimination, which we have discussed in my earlier video. Then we have Benzyne mechanism, that is elimination addition reaction mechanism. Then SN1 mechanism and SRN1 mechanism, which has a radical ion as the intermediate. Now Benzyne mechanism, as I said a couple of seconds back, that it happens for those aryl compounds which do not have any activating groups on it. Alright, there is no electron withdrawing group or activating group on it. The requirement here is a presence of a very strong base. That's required. If there is a very strong base present, then even without the presence of an activating or an electron withdrawing group on the ring, we can carry out nucleophilic substitution reaction via Benzyne mechanism. Now this also again is a two-step mechanism. The first step involves the elimination, that is the removal of the halogen along with proton, or removal of the leaving group along with the proton on the ring, followed by then during this step the benzyne intermediate will be formed. This is followed by addition of the nucleophile onto the ring. The nucleophilic attack will happen and you get the product. Now an example to understand the mechanism, we are taking orthochlorotoluene has been treated with sodamide. Okay, you are taking very strong base, sodamide in liquid ammonia. You get these two products. Alright, you get two different regioisomers, you can say. The incoming amino group attacks the ortho position as well as the meta position to the substituent, or to the CH3, or you can say the incoming nucleophile attacks the ipso position and the sine position. Now here what happens is the amide, the nucleophile, first abstracts the proton, and the electron on the CH bond is transferred to the ring, and the chloride ion is also removed and it goes off. You get ammonia and Cl. Alright, and this is the benzyne with an alkyne or a triple bond on the aromatic ring. Now, once this benzyne is formed, so this is the elimination part, HX has been removed. Next is the nucleophile. Now, the incoming nucleophile can attack either on the ortho position to the methyl group or meta position to the methyl group. So, if this incoming nucleophile attacks the ortho position of the methyl group, you will get this as the product. And if it is attacking the meta position, then you will get this as the product. So you see here, you can see two regioisomers are formed. Now, it is because of this benzyne that you get two regioisomers. That's a proof of the formation of benzyne. If benzyne has not been formed, you will not get such regioisomers. Alright, now we'll see what is the evidence. Now, when chlorobenzene was treated with potassium amide, it gave two regioisomers. This was what you can say, the chlorobenzene was labeled chlorobenzene, and we could find that the amino group was introduced to the labeled carbon as well as to the unlabeled carbon, adjacent carbons, one on the amino group. This was 50-50 attack, and one is the ipso substituted product and the other one is the sine substituted product. Ipso substitution means the nucleophile attaches or is introduced or attacks the carbon to which the leaving group is present. And sine substitution is the nucleophile attacks the carbon adjacent to the carbon to which leaving group is present. Okay, so formation of ipso compound and sine compound, or ipso product and sine product, is an evidence for the benzyne mechanism. Another evidence is the when you treat this same chlorotoluene with potassium amide, you are getting ortho product as well as meta product. You are not getting para product. So the benzyne, the triple bond is formed between the ortho and meta carbon and not between para and meta or something like that. So it means the benzyne is, this benzyne mechanism is involved, or the benzyne intermediate is involved. You're not getting the para product. Alright, so another evidence is when you carry out the reaction with substrate wherein all the when both the ortho position and the para position are blocked by the substituent, no reaction happens. See, the two ortho positions of the bromine is being blocked by substituents, so benzyne cannot be formed over here. Actually, the benzyne has to be formed over here or over here, so that's not formed. So this is another evidence that benzyne mechanism is followed here. See the temperature here, minus 30 degrees. You need to use only mild temperature if you are using a strong base to carry out the nucleophilic substitution reaction. Now we'll see the regioselectivity of benzyne mechanism, or the regiochemistry of benzyne mechanism. Now, as we discussed just now, if there is no hydrogen ortho to the leaving group, the reaction will not happen. So, presence of ortho hydrogen on the substrate is important. Alright, because benzyne has to be formed by removing the ortho hydrogen. So, this will not happen. This reaction will not happen. Another regioselectivity of the benzyne mechanism is, if there is no electron withdrawing group as a substituent on the substrate, then you get mixture of regioisomers. See, you get the para product as well as the meta product. If the substituent is not electron withdrawing, like methyl group, then you will get mixture of regioisomers. Now, if the substituent is an electron withdrawing group, that will direct the incoming nucleophile. Alright, so if the electron withdrawing group is present ortho to the leaving group, then the nucleophile prefers the meta attack. Okay, you get meta product, because when nucleophile attacks the meta position, the negative charge will be introduced onto the carbon which is nearer to the electron withdrawing group. So the carbanion will be more stabilized when there is meta attack. If it is an ortho attack, what will happen? The negative charge will be away from the electron withdrawing group. So it will not be as stabilized as when we have the carbanion due to meta attack. So, the electron withdrawing group is directing the incoming nucleophile to attack the meta position. Now, if the electron withdrawing group is present meta to the leaving group, okay, this is the early cases, the electron withdrawing group and the leaving group are ortho to each other. Now, if the electron withdrawing group is present meta to the leaving group or para to the leaving group, then you will get the benzyne, the triple bond between para and meta carbons, and the nucleophile will be directed to attack the para position rather than the meta position. Because when the nucleophile attacks the para position, the carbanion, the negative charge, will be on a carbon which is nearer to the electron withdrawing group. If the attack was on the meta position, then the negative charge will be farther away from the electron withdrawing group. So that is the directing nature of the electron withdrawing group, which decides the regiochemistry of the reaction. We shall take examples and see how this is happening. Now, you have this parachlorotoluene. You get mixture of a product, both para product as well as the meta product. Now, you introduce an electron withdrawing group instead of the toluene over here. You are introducing CF3. Then, CF3 is present para to the leaving group. You will get more of para product than the meta product. Para attack is favored. Alright, and if you introduce methoxy group, again the para attack is favored. Alright, so this is because the attack at the para position helps or makes the negative charge to be present nearer to the electron withdrawing group, which will stabilize the carbanion. So this is the case when the substituent is present para to the leaving group. Now when the substituent is present ortho to the leaving group, say for example orthochlorotoluene, again orthochlorotoluene will give us meta and ortho product, same as parachlorotoluene, which gave us a mixture of product. But when you introduce an electron withdrawing group instead of the methyl group, the ortho product, the substrate will favor meta attack rather than ortho attack. So we do not observe ortho attack, or ortho product is not formed. Again, it is the directing nature. This shows the directing nature of the electron withdrawing group. So electron withdrawing group, the incoming nucleophile, will direct the nucleophile to attack the meta position. When the leaving group is present, ortho to the electron withdrawing group. Same is the case when the leaving group is present, meta to the electron withdrawing group. Now, there are other methods of preparation of benzyne. That is, benzyne intermediate can be formed from all these precursors. Not only the aryl halides, but if you have such substituents on the aryl ring, you can easily produce benzyne. So you can produce benzynes under mild conditions. That's important. So these are the ways by which you can bring out, or you can produce benzynes under mild conditions, or else you'll have to use drastic condition like very strong base. Now let us see a few examples related to these precursors, benzyne precursors. See, you have anthranylic acid. This on diazotization will give you the diazonium salt, this salt. Okay, and then easily this nitrogen and the CO2 will be removed and you get the benzyne. So from the diazonium salt, you can easily remove the nitrogen and the carbon dioxide. So from starting with anthranylic acid, you can end up with the benzyne, and then you can carry out the nucleophilic substitution reaction. Similarly, triazole derivative here, you oxidize this triazole derivative, it will lose 2 nitrogen molecules and you get the benzyne. Okay, you are oxidizing the 1-amino benzotriazole. You get benzyne. So simple oxidation will do, mild conditions. Okay, and similarly here, decomposition of benzothiazole 1,1-dioxide. Here this also, simply heating, sulfur dioxide and nitrogen will be removed and you get the benzyne. And all these can be carried out for nucleophilic substitution reaction. See, the product which you get will be free from all these substituents present on the substrate. The beauty of this is that you need to use only mild conditions. That is, you need not go for strong base, presence of strong base or high temperature or anything. You can use mild conditions. Particularly diazotization, you need to carry out 0 degree centigrade to 5 degree centigrade. So between that range. So such mild conditions you can, the reaction can be carried out. Now let us see a few examples, few reactions which involves benzyne intermediate. So in the absence of a nucleophile, if benzyne is formed, it will dimerize to give you biphenylene. Alright, so this follows the 4+2 cycloaddition reaction. There are a lot of reactions wherein 4+2 cycloaddition is happening with the benzyne instead of the nucleophilic addition. So here you have a Diels-Alder reaction. A Diels-Alder adduct is formed, wherein which on reduction followed by acid workout, you get the naphthalene. So this is an important reaction to produce naphthalene. Synthesize benzyne or in situ, and then you have furan, you get this adduct, and then reduce it, you get the naphthalene. Okay, so these are not nucleophilic reaction exactly, but the reactions of benzyne. Alright, instead of these diene, if you introduce a nucleophile, it becomes nucleophilic substitution reaction. Another similar 4+2 cycloaddition, you get a derivative of naphthalene over here. Here you are not using furan, but you are using cyclopentanone derivative, and you get this naphthalene derivative. Alright, now another reaction again with anthracene, again you are getting adduct, Diels-Alder adduct. So 4+2 cycloaddition reactions happen with benzyne very easily. Now this is carbanion attack. This is a nucleophilic reaction. This this carbon is acidic over here. The hydrogen, this methylene hydrogen is acidic and can be easily removed by the base, and this will replace the bromine, and you get the nucleophilic substituted product. Okay, that is a reaction with carbanion. A CC bond is formed. See that here you have the mechanism. This carbanion formed will attack the benzyne, and you get a product. Alright, now another one is important reaction is homocyclic ring closure. Again, it is a nucleophilic substitution reaction. So this carbon, you can see the mechanism over here. The benzyne is formed here with the removal of HCl, and once the benzyne is formed, after that, this carbon, this hydrogen is acidic here, this proton is acidic, it can be removed, and then ring closure happens. So you have 1, 2, 3, 4, 4-membered cycle is formed. So intramolecular ring closure or homocyclic ring closure happens. Alright, yet another example for homocyclic ring closure. Here you get 6-membered ring formed. Okay, so here this carbon, the hydrogen between the two carbonyl carbon is acidic, and that combines with reacts with the benzyne formed here. This HCl will be removed and this will attack here, and you get the 1-acetyl 2-tetralone. So these are the reactions. Let us have a look at the structure of benzyne. In benzyne, all the carbons are sp2 hybridized, all the carbon atoms are sp2 hybridized, and the pi electron system of the original ring, or the initially what was a pi electron system on the aryl ring, that is not altered when an extra pi bond is formed. Alright, and the proton is removed. Since the proton is removed from the ortho position by the base, the ortho carbon has a filled sp2 hybrid orbital, and when the halogen or halide is expelled by the carbanion, there will be an empty sp2 orbital adjacent to each other. So these two will overlap with each other, but these two orbitals, this empty orbital and the filled orbital, are placed 60 degrees away from each other. Okay, they are not parallel. So you can see here they are placed 60 degrees away from each other. They are not parallel. So these two orbitals overlap to form the new pi bond in benzyne, resulting in the formation of the benzyne. Now these two will not take, this bond will not take place in the resonance of the ring. Okay, so here you have the pi orbital of benzene. This new bond will not take part in the resonance of the ring. They will remain outside the ring, or rather outside the ring. Alright, now because of this, effective overlapping is not possible. Since it is 60 degrees apart, the effective overlapping is not possible, and hence they are more weak. This pi bond is weak, and that's why they are very reactive. Highly reactive. Benzyne is highly reactive. Okay, since the newly formed pi bond do not take part in the resonance, and they are weak because these orbitals are placed 60 degrees apart. Now, benzyne usually cannot be isolated under ordinary condition, since they are highly reactive. As soon as it is formed, it will react with the nucleophile, or it will undergo dimerization, but it has been isolated in argon at 8 Kelvin, a very low temperature. And as I said earlier, there is no formal triple bond, and this triple bond will not contribute to the resonance structure, and this will not affect the aromaticity of the ring. So, and the spectral studies show that the structure A is more predominant than structure B. That is, the newly formed bond is outside the ring. It will not contribute, or it will not take part in the resonance. So structure A contributes more than structure B. So that's regarding the structure of the benzyne. So here we have seen how the benzyne mechanism operates, and how the benzyne, what are the various reactions of benzyne. and also the structure of the benzyne. Thank you.